Okay, so in this video we're going to take a look at the ratio test. All right, so now the ratio test, as we can see, it's here in front of us. So we start with a series with the non-zero terms. All right, so here they could be positive or negative, right? So this will work for alternating series as well. All right, and we take a look at the absolute value of the n+1 term over the n term. And we evaluate the limit as n goes to infinity. All right, and what we're looking for is one of three things can happen, right? So we're going to break this down since it is the absolute value, right? So we're going to get a positive, and this Greek letter you see here, that's rho, right? They just define rho as the limit of that. So if the value of this limit, which we're calling rho, is bigger than or equal to 0, but less than 1, then we can say the series converges absolutely. If the value of rho is greater than 1 or infinity, right? If the limit itself equals to infinity, then we say the series diverges. Now the third case would be if rho is equal to 1, then the test does not provide any information, right? In other words, inconclusive. Okay, so what the ratio test here is measuring is how the ratio of the next term and the previous one, how fast they're going to 0 or not, right? And when it's 1, it doesn't really give us any information, right? And we can think of any p series, really, if you take the ratio, right, of the p series of any p series here, right? So, for example, here, right? So what that would look like is the limit as n goes to infinity, right? This rho is 1 over n+1 over 1 over n. And here that becomes what? N over n+1 limit as n goes to infinity, which is 1. Which we know already from previous tests that we've used, this diverges. And we could see that for this, right, if we apply the ratio test, the limit as n goes to infinity, and we get the same thing, 1 over n+1 squared over 1 over n squared, and then this becomes the limit as n goes to infinity of n squared over n+1 squared, which again also is 1. Right, but we know here from other tests that we've applied that this converges. Okay. All right. So that's kind of the idea why really we could see that, in these two examples, right, we come away from the test as it just being inconclusive, right? It just does not apply here. But if we are in the other two cases, right, then we can make a conclusion about our series. So let's start off with some examples here. Or let's do some examples. So let's take a look at this series here. N is equal to 1 to infinity of -2 to the n over n squared. Okay. All right, and I'm going to apply for these the ratio test. All right. Now, one thing when we have this -2, this is an alternating series, right? You can think of that -2 as -1 to the n, 2 to the n, all right, n squared. All right, so when I apply the ratio test, right, I take the absolute value of the next term over the previous term, then I can just drop that -1 to the n, right? Because I'm only the absolute value, we're strictly looking at the positive result of that limit, right? So my rho is going to be the limit as n goes to infinity. And the way I'm going to write this is I'll write 2 to the n+1 squared. And when I take a ratio, division of fractions is nothing but multiplication by the reciprocal. So I can write this as times the nth term, which would be n squared over 2 to the n. All right, and then from here, the goal is to evaluate this limit. Now I drop the absolute value signs because every term here is positive. right? Since I'm only looking at values that start at 1 and go towards infinity, and that -1 is not part of my limit already, so I don't need the absolute value here. Okay, so here, as I simplify here, so we have 2 to n plus 1, so we get the limit as n goes to infinity of 2. All right, n plus 1 minus n, we subtract the exponents, the n's go to 0, and we're just left with 2 to the first power, and then over n squared, n plus 1 squared. Okay, and then we see here as n goes to infinity, this term goes to 1, but we have a 2 here. So the overall limit converges to the value of 2, right? The limit converges to 2. But if we go here to our test, right, we're in case 2 here. Rho is, in fact, bigger than 1. So that tells me that the series diverges. So what we have here is we have a divergent series. All right, let's take a look at another example here. So here, let's see, we let the sum of n over 5 to the n, and starting at 1 to infinity. So applying our ratio test, right? And again, n is always positive, so when I write the limit, I don't need to put the absolute values because the values themselves are always positive. So I'll start off here, again, n plus 1, the next term, 5 to the n plus 1, and then times 5, the reciprocal, 5 to the n over n. All right, and then we have the same thing here, right? As I reduce, we'll be left with the limit as n goes to infinity, 5n minus n plus 1, we get 1/5 times n plus 1 over n. This is constant as n goes to infinity here. This reduces to 1. So we're left with 1/5 times 1, or 1/5. And again, looking at our results here for our ratio test, we see we are in the first case. Rho falls between 0 and 1, so it converges absolutely. All right, so the series here converges absolutely. Okay. All right, and again, as a reminder, what that tells us is that also the if this made this an alternating series, -1 to the n, that would also converge as well, right? Because we have absolute convergence here. All right, let's try one more example here. Now, the ratio test is helpful when we have like factorials as well. Right? It lends itself to simplifying those, right? As long as we are comfortable working with factorials. So let's say here we add this. So let's say this was our series, all right? N factorial, the whole factorial squared, and again, what that means is n factorial, sum to infinity, n factorial times n factorial, all right? And then over 2n factorial. Okay, so let's start again. We'll set up our ratio test. So the limit as n goes to infinity. Now again, be careful here how you plug in that n plus 1. Right? Let's keep in mind our order of operations here. So here we'll have n plus 1, right? That whole quantity factorial, and then that squared over 2n plus 1 in the factorial of that, right? So that's the n plus 1 term, and then the previous term, the nth term, right? So the reciprocal here, we have 2n factorial over n factorial squared. Okay, so here is where our knowledge of working with the factorial is going to come in handy here. All right, so remember 5 factorial is 5 times 4 times 3 times 2 times 1, etc. But you can also stop along the way and write it as 4 times 3 factorial, or 4 times 3 times 2 factorial. All right, so just keep that in mind, right? These are all representations of 5 factorial. So I'm going to use that here. Well, one thing to realize here, right, the bottom, one more intermediate step here before I start simplifying. So here we'll have n plus 1 factorial squared. I'll distribute that too, so we get 2n plus 2 factorial. All right, times 2n factorial over n factorial. All right, so now I'm going to expand in the first term here. All right, so I'll expand the limit as n goes to infinity of n plus 1 times n factorial, right? Because that would be minus 1, right? N plus 1 times minus 1 leaves me at n factorial, that whole quantity squared. And then here we'll start with 2n plus 2, subtract 1, 2n minus, plus 2 minus 1, so 2n plus 1, and then subtract 1 again, and then that's just 2n, and then I'll stop there. Right, and you'll see why in a second. So when I multiply that, 2n, there should be a squared here, 2n factorial over n factorial, whole quantity squared. Okay. All right, and now we could see by stopping where I did, I can simplify some things out, right? So here, that simplifies to 1, right? The squared here also simplifies to 1. And now what's left here? The limit. Now be careful here, right? N plus 1, no more factorial, but that whole quantity is squared. All right. Okay, so there's squared here, but that squared also goes here. So it's n plus 1 squared. All right, and in our denominator, we get 2n plus 2, and 2n plus 1. Okay. So now I notice here I have now a rational type function where the degree on top is squared, 2, I should say, and so is the degree at the bottom, right? So here, if you're not seeing this right away, you could expand everything, but I'm not going to do that. Instead, what I'm going to do is I'm going to factor out. So if I factor out an n here, I'll be left with 1 plus 1 over n, but keep in mind, right, that whole quantity is squared, so when I factor it out, it's not just n, it's n squared. Okay. And then here, when I factor out a 2n, I could factor out a 2n here, and we get 1 plus 2 over 2n. And then here, if I factor out another 2n, we get 1 plus 1 over 2n. Right, each one of those terms has a 2n. Now let me clean this up a little more here. I'm going to rewrite this as the limit as n goes to infinity of n squared, and here we get 2n times 2n, we get 4n squared, 1 plus 1 over n squared, over 1 plus, simplifying here, 1 over n, times 1 plus 1 over 2n. All right, and now we can see as n goes to infinity, well, first of all, these reduce, right? As n goes to infinity, these ratios, 1 over n, 1 over 2n, all of those go to 0. Right, so which means we're left with 1 plus 0 over 1 plus 0, 1 plus 0, and then there's last thing here, this is 1/4, right? Don't forget that 1/4 there. So we have 1/4, the final result here. All right. And now we could see here, we go consult our ratio test here. This is the first case, right? Rho falls between 0 and 1. So what that tells me is that our series that we started with, right? Sum n factorial squared over 2n factorial absolutely converges, or converges absolutely.